This training details the signalized intersection analysis in the highway capacity software. In this module, the signalized intersection analysis process will be discussed. All analysis will be done using the Streets module in HCS. This training video will cover creating a new file, data input, signal timing optimization, and reporting using the Streets module. As used in several other training modules, the sample project of State Route 315 from North Broadway to north of Bethel Road will be used for this demonstration. Because this module involves signalized intersections, the area of focus will be the intersections of Henderson Road with Olentangy River Road and with State Route 315 northbound ramps. When a new file is created, the analyst may choose either the classic mode with all of the required inputs presented in tabular style interface or the visual mode. The visual mode presents a grid where the user may draw nodes or intersections and the links connecting them. When the user selects a link or node and then right-clicks, a series of dialog boxes appear that mimic sections of the classic mode interface. In these dialog boxes, the data can be entered and edited. For the purposes of this training, the classic mode will be selected. After selecting to start a new file, this Quick Start menu pops up. In this menu, the analyst can specify the number of intersections to be evaluated, along with several other global input parameters. For an isolated intersection analysis, the number of intersections is 1. For an urban street segment or facility, the total number of signalized intersections is entered in this box. In the case of the sample project, there are 2 intersections, so 2 is entered into this box. The forward direction is assigned to the direction of the major street through movement that corresponds to the NEMA movement 2. In this case, the eastbound phase at the major intersection, Henderson Road at Olentangy River Road, is phase 2. Therefore, this forward direction is set to eastbound. This direction should be consistent with the direction of the corridor. So, in the case of our sample project, the only acceptable directions would be eastbound or westbound. If phase 2 from the existing timing plans in the sample project would have been on the northbound or southbound directions, the forward direction would still need to be eastbound or westbound, and the analyst could choose either one. HCS defaults to a single period analysis with an analysis duration of 15 minutes. Then, the program employs the peak hour factor to adjust the total 60-minute demand volume to an equivalent hourly volume for the peak 15-minute period. Therefore, the number of periods should be set to 1 with the analysis duration set to 0.25 hours. The base saturation flow rate is based on the location of the project. If it is an urbanized area, the base saturation flow rate is 1,900 passenger cars per hour per lane. Otherwise, the base saturation flow rate is 1,750 passenger cars per hour per lane. Refer to section 5.3 of the OATS manual for more information on setting base saturation flow rates. Because the sample project is in an urban area, the base saturation flow rate is 1,900 passenger cars per hour per lane. The posted speed limit may be entered globally on this screen. In the sample project, the majority of approach speed limits is 35 miles per hour. This value can be changed in the next window if needed. The signal timing inputs can be globally set. Refer to section 5.7 of the OATS manual for more information regarding signal timing inputs. In some cases, the minimum green, yellow change, and red clearance intervals differ by approach or movement. In the case of the sample project, the cycle length is set to 120 seconds with all approaches having a yellow change interval of 4 seconds and a red clearance interval of 2 seconds. The minimum green is set to 7 seconds but will need to be modified in the next input screen for the through movements. These values will also be modified during the signal optimization process. The default values for passage time and detector length can be used for most, if not all, analysis. The default passage time is 2 seconds while the default detector length is 40 feet. Once clicking OK on the Quick Start menu, a warning will pop up regarding the forward direction. The warning states, the urban street forward direction has been specified as eastbound. Once this direction has been chosen, it can only be reversed from now on in this particular data set. Northbound and southbound will no longer be available for selection in this data set. Are you sure you want to proceed with eastbound as the forward direction? After confirming that this is the correct direction, is the corridor eastbound, westbound, the analyst can click Yes. Before getting into detail on the inputs, we want to point out the Help menu. Pressing F1 while on any input box will display information on that input topic. Also, by clicking on the question mark icon at the top of the toolbar, a series of options appears. By clicking on Contents, a new information window opens. The analyst may use the Getting Started, General Controls, or Operational Data portions of the Contents window to learn more about each of the required inputs for the analysis. This guide can help the user understand more information about each input, but the analyst should always refer to the OATS manual for ODOT's specific preferences regarding these inputs. The data inputs on this page are for the first intersection. To toggle between intersections and input intersection-specific data, use the drop-down menu next to Intersection on the top toolbar. To set the analysis time period, enter the hour in the Start Time window. In this case, we will be analyzing the PM peak, so we'll set the time to 1700. The specific start time does not need to be coordinated with the actual peak hour. Defaults of 700 and 1700 can be used for the AM and PM peak hours, respectively. For example, even if the PM peak hour is 5:15 to 6:15, it is acceptable to put the start time in HCS as 1700. As long as the hourly volumes inputted into the program are from 5:15 to 6:15, the time in HCS does not matter. It is just helpful to be able to distinguish between analysis periods within the HCS files. Now it's time to start entering the data for each study intersection. For the purposes of this training module, we're going to focus on just the intersection of Henderson Road and Olentangy River Road. There are features of the intersection with the State Route 315 northbound ramps that will be discussed, but the primary focus will be Olentangy River Road. The urban street, intersection, and description are based on the location and details of the project. In this project example, we are studying the Henderson Road corridor, so the urban street is Henderson Road. The segment length can be entered by clicking on the All Segment Lengths button, which brings up a new box. In this case, there are only two intersections, so only one segment between them. The measured distance between the centers of each intersection is 463 feet, which is entered into the box for the segment length between intersections 1 and 2. The existing peak hour factor for the intersection should be entered in the peak hour factor box. If the existing peak hour factor is unknown, a default peak hour factor of 0.92 should be used. Refer to section 5.2 for more information on peak hour factors. The final step under the general heading involves setting the lane configurations. Lane use arrows can be toggled using the gray buttons around the edge of the intersection schematic figure. Lanes need to be set by approach. The hourly demand for the PM peak hour should be entered by movement. These values represent the hourly volume for the peak hour. As a reminder, the program employs the peak hour factor to adjust the total 60-minute demand volume to an equivalent hourly volume for the peak 15-minute period. The storage links for each movement should be measured using aerial imagery for each movement. If recent aerial imagery is not available, construction plans may be used, or the links may be field measured. Details on measuring storage links are provided in the next slides. For turn lanes, the length begins at the stop bar and extends to where the full width lane ends, as illustrated in this graphic. The taper length is not included in the length of the storage lane. To measure the storage lengths for through lanes, the distance to the upstream intersection is measured. In the case of the eastbound through lane at the Olentangy River Road intersection, the storage length is measured to the far edge of the crosswalk at Lower Land Drive. This distance represents the respectable length for traffic to queue, which in this case is no further than the edge of the crosswalk. Traffic should not queue through the crosswalk. This graphic illustrates the storage length calculation for the northbound through movement. For illustrative purposes, north is to the right on this illustration. South of Henderson Road, the next closest signalized intersection is nearly 4,400 feet away. There is a low-volume residential intersection at Tedderidge Road, located 500 feet south of Henderson. However, it is not uncommon for traffic to queue through a low-volume residential intersection such as this. Given the long distance to the signal at Highland Drive, A storage length of 2,000 feet was arbitrarily entered for the northbound through movement. Ultimately, this location has sufficient storage. Operations for this approach will be based on LOS and delay rather than queue links. Another unique situation is the channelized right turn along the westbound approach. As illustrated here, the bridge over State Route 315 limits the storage length for this turn lane, and the right turn lane widens out immediately west of the bridge. The storage lengths for channelized turn lanes is measured from the point it begins a full width lane to the point that it joins the cross street. In this case, the storage length is 320 feet. When reviewing the HCS output, the queue in the through lanes should be examined to make sure they are not blocking the turn lane. If they are, then microsimulation may be required. The saturation flow rate is detailed in section 5.3 of the OATS manual. In urban areas, the default saturation flow rate is 1,900 passenger cars per hour per lane. In other areas, the saturation flow rate is 1,750 passenger cars per hour per lane. Because the sample project is in an urban area, the default saturation flow rate of 1,900 passenger cars per hour per lane is used. The heavy vehicle percentage should be entered based on calculated values from the existing traffic counts. Heavy vehicle percentages should be entered by approach, not individual movement. For more information, see section 5.5 in the OATS manual. Grade should be considered when it exceeds 3% for more than half a mile. In most cases, the grade will be level or 0%. For more information regarding grade, refer to section 5.1 in the OATS manual. Pedestrian counts should only be included in the analysis if the study location is in an area with a lot of pedestrian traffic. Examples may be in central business districts or around college campuses. In the case of the sample project, the default of 0 pedestrians per hour will be used for this analysis. The arrival type is a factor applied to the platoon ratio used to describe the quality of signal progression through the corridor. The platoon ratio is the demand flow rate during a green cycle phase divided by the average demand flow rate during the whole analysis period. An arrival type of 3 should be used for all intersection analysis. The use of an arrival type other than 3 must be approved by ODOT and documented in the project analysis documentation. An arrival type of 3 represents a platoon ratio of 1. The upstream filtering adjustment factor, I, accounts for the effect on vehicle arrivals from an upstream signal. The upstream filtering adjustment factor ranges from 0.09 to 1, and a value of 1 is appropriate for an isolated intersection. The analyst must enter this value in HCS when evaluating a single intersection, but the value is computed automatically by the software within an urban street analysis involving multiple intersections. If signal spacing is greater than 3,200 feet, the intersection is considered to be operating in isolation and a value of 1 is used. Guidance on use of the upstream filtering adjustment factor is provided in the HCM chapter on signalized intersections. For ODOT projects, an upstream filtering adjustment factor of 1 should be used for all isolated intersection analysis, for example, the analysis of a single intersection. When multiple intersections are evaluated in a single streets file, the analyst should allow the I factor to calculate automatically based on the VC ratio of the upstream signals. The initial queue, expressed in number of vehicles for the lane group, specifies the queue at the beginning of the analysis period, either observed in the field or carried over from the computations of a previous period. It represents the number of vehicles present in the movement group at the start of the analysis period and should not include vehicles in queue due to random, cycle-by-cycle fluctuations. When demand exceeds capacity for a given analysis period, the incremental unmet demand is carried over as the initial queue for the following period. Existence of an initial queue implies that demand exceeds capacity for that lane or movement group in the previous period. When this condition exists, the analyst may need to use Transmodeler instead of the HCS and should consult with ODOT early in the study process. Initial queue should be entered as 0 for all intersection analysis. The speed limit is set per approach based on field conditions. In the quick inputs, the speed limit was globally entered as 35 miles per hour. However, the eastbound approach has a posted speed limit of 50 miles per hour. Therefore, the speed limit for the eastbound approach was changed in this window. The right turn on red flow rate is a difficult parameter to estimate and can have a quantifiable impact on the analysis results. The right turn on red is expressed as an hourly flow. The HCM methodology subtracts the right turn on red demand from the initial demand input before the adjusted flow rate is computed. The right turn on red value should be 0 for all intersection analysis. At locations where right turn on red movements are a significant component in the intersection operations, Transmodeler may be a more appropriate tool. The methodology allows the analyst to include an unsignalized movement, like a channelized right turn, in the signalized intersection analysis. This is done by selecting the unsignalized movement checkbox for the qualifying movement. When unsignalized movement volumes are low, any delay associated with them will be low and typically can be ignored. If unsignalized movement volumes are high, it may be more appropriate to analyze the intersection using Transmodeler. For ODOT analysis, the unsignalized movement checkbox should be checked, and the right turn volume entered for all free yield right turn movements. Unsignalized delay field will be 0. The default values for lane widths, buses, parking, bicycle volumes, and detector lengths can be used for ODOT analysis. If these factors are changed from the default values, documentation is required. For more information on these factors, refer to the interrupted flow chapters of the Highway Capacity Manual. The phasing information can be entered from the existing signal timing plans provided by the maintaining authority. If not readily available, the analyst may also field measure the timings and associated phasing configuration. Typically, standard NEMA phasing can be used if phase numbers are unknown. The uncoordinated intersection checkbox flags an intersection to be analyzed as an isolated intersection instead of as a part of an urban street facility. Checking the field measured phase times tells the program that the inputs recorded for the phase split times indicate the field measured actuated splits. When this box is checked, the user overwrites the program calculated actuated phase splits based on the travel demand. Most of the time, this box will be unchecked. For more information on these inputs, refer to the HCS Help menu or the OATS manual. The phasing wizard can be used by the analyst to define the phasing scheme in the NEMA dual ring format. After selecting which phases are protected and permitted, the appropriate phase numbers will be assigned to the movements. For protected, permitted left turn movements, such as the case with the eastbound, northbound, and southbound left turns in the sample project, yes should be selected for the protected left turn phase and the permitted left turn phase. Because the westbound left turn phase is protected only, the permitted phase box is not checked for this movement. Similarly, right turn overlaps can be assigned. Phase splits are entered for each lane group, where a phase split represents the sum of the green, yellow change, and red clearance intervals for the phase. The entered phase split should be the maximum phase split from the provided or field measured signal timings. If the subject intersection is new and phase splits are not known, the analyst may estimate the maximum split times. The analyst should ensure that value entered for phase split is greater than the sum of the minimum green, yellow change, and red clearance intervals. It should be noted that the values for the phase splits differ between the entry boxes under the timing header and the split times in the phase duration box. In this example, the intersection phases are actuated, meaning they will likely not have the same duration every cycle. The timings in the phase duration represent the average phase duration over the analysis period. The phase split represents the maximum split time allowed for that movement, even if there is an unserved demand. Had the pre-time signal or field measured phase times box been checked, these numbers would match. The yellow change and red clearance intervals should be entered based on existing timing data. If such data is not available, defaults of 4 seconds for yellow change intervals and 2 seconds for all red intervals shall be used. See section 5.7 of the OATS manual for more information on these inputs. The minimum green times should also be entered based on the existing timing plans. If the existing timing plans are not provided, a minimum green time of 20 seconds should be used for main line through movements, 10 seconds for side street through movements, and 7 seconds for left turn movements. Refer to Section 5.7 of the OATS manual to learn more about the minimum green inputs. If there is a lagging left turn phase, the checkbox next to the appropriate movement may be selected. Be careful not to create a yellow trap as discussed in Section 5.7, which occurs when one protected permitted left turn phase lags an approach with a leading protected permitted left turn phase. The yellow trap and ODOT preferences on lagging left turn phases are discussed in detail in Section 5.7 of the OATS manual. When the signal is selected to be actuated, such as is the case in this sample project, the coordinated phases are automatically selected to be minimum recall. Other phases can be selected to have maximum or minimum recall modes. When the signal is selected to operate in pre-timed mode, all approaches are set to maximum recall modes. For the vast majority of ODOT projects, the passage time, dual entry, Dallas and flashing yellow arrow phasing, and simultaneous gap inputs will remain as default values. The need to deviate from these default inputs is very rare and should be documented. The information included under the General tab includes the name of the analysts and their agency and the analysis date, the analysis time period, which is usually the AM or PM peak, and the analysis year are also entered. An entry for the jurisdiction is also provided and commonly refers to the location or client. Under the second general header, just below the project information entries, the only factor that needs to be changed from default is the queue length percentile. The analyst must select this length to be the 95th percentile instead of the default 50th percentile. All other factors in this screen should remain as the default values. The lane information under the intersection header should be populated based on the information completed in the primary input data windows. At the intersection of Olentangy River Road and Henderson Road, there are no shared lanes. Therefore, the percent of turns in the shared lane boxes are grayed out. The study intersection of Henderson Road with the State Route 315 northbound ramps does have a shared lane, so let's look at those inputs for these factors. At the intersection of Henderson Road and State Route 315 northbound ramps, the northbound approach has a shared through and left turn lane along with an exclusive left turn lane. Under the shared lane row, the box is checked under the northbound left turn. Then the percent turns in the shared lane must be entered based on traffic count observations. Refer to Section 5.6 for information regarding lane utilization measurements and inputs. In this case, it was determined that 45% of the left turn volume from the State Route 315 northbound off-ramp uses the shared through and left turn lane, so 45 was entered under the northbound left movement. Notice that the westbound right turn movement is in a shared through and right turn lane. However, because that lane is the only lane that can turn right, 100% of the right turns must be made from this lane. Therefore, this box is grayed out under the westbound right turn movement. Because of the close spacing between Olentangy River Road and State Route 315 northbound ramps, vehicles do not evenly use the eastbound through lanes at the Olentangy River Road intersection. Therefore, the lane utilization was measured using video footage when the traffic counts were collected. In this case, 600 out of the 920 vehicles used the heavier lane. Notice, the heavier lane is not specified as part of this analysis. It is just important to note the number of vehicles in the heavier of the two lanes. For most analysis, the lane utilization will be fairly evenly distributed, and entries for the heaviest lane volume will not be necessary. Only when there is a lane use imbalance would entries in these boxes be necessary. There are several other inputs on this screen that can typically remain as default values. The pedestrian walk and clearance intervals are only used when there is a high level of pedestrian activity. Even then, the walk and clearance intervals can be accounted for by increasing the minimum green times for the vehicle phases to include the pedestrian clearance interval. Also, the opposing right turn lane influence may be needed at locations with permitted left turn movements being influenced by a high volume exclusive right turn lane on the opposing approach. Microsimulation may be required to evaluate this condition if there is a significant amount of right turning traffic and the opposing approach does not have a protected left turn phase. HCS contains a robust traffic signal timing optimization toolset that includes optimization of cycle lengths, phase splits, and offsets for a variety of objective functions. While there is a quick optimization function for ODOT projects, the full optimization process should be used. By clicking on the clock symbol at the top of the toolbar, the full optimization window opens. This window is specific to each intersection. If a corridor is being analyzed and an intersection should not be included in the optimization, the box for Include this intersection in optimization should be unchecked. As previously stated, there are a number of possible objectives when optimizing signal timings using HCS. For the purposes of ODOT projects, balanced delay should be selected from the drop-down box. The analyst can then select what features should be optimized: cycle lengths, splits, and offsets, or some combination. In some cases, the analyst may not want to change the cycle length because the intersection is part of a larger coordinated system, and the cycle length must remain the same. As illustrated here, if the cycle lengths are optimized, the splits and offsets will also be optimized as evident with the grayed out boxes. Per ODOT guidelines, the minimum acceptable cycle lengths range from 60 seconds to 120 seconds for most intersections. In case of oversaturated intersections, a higher cycle length may be warranted. While not an official ODOT policy, the general rule of thumb for cycle lengths is that they are in increments of 10 seconds. It is rare for an intersection to have a 95-second cycle length. In most cases, the intersection would have a 90-second or 100-second cycle length. The master intersection can be selected by indicating its number in the HCS program. In the case of the sample project, intersection 1 is the intersection at Olentangy River Road. By setting this location to be the master intersection, the optimized offset for this intersection will be 0 seconds. A minimum of 50 generations is required for ODOT projects, and using the default of 200 is acceptable. Signal optimization is an iterative process. The number of generations represents how many iterations the program will run before deciding on optimal signal timings based on the objective function. In many cases, it is acceptable and even desired to set the minimum number of generations higher than 50. Typically, 3 or 4 optimization runs may be necessary to get the best results, as each run begins with the previous results and further refines them. Population size, crossover probability, mutation probability, convergence threshold, and random seed number inputs can all remain as default values. This information is related to the statistical algorithms used when optimizing signal timings to meet the objective function. Prior to running the optimization, it is important to check the diagnostic message pull down to check for warnings. Once the inputs for all intersections being optimized are entered in the program, the analyst should press the green Start button. A new window like the one on the left will open showing the progress of the optimization. When the optimization analysis is complete, the window like the one on the right will open and will provide the level of improvement provided by the optimized timings. Hitting Save will populate the optimized signal timings into the phasing inputs under Primary Input Data. For this example, the optimization terminated because the maximum number of generations was reached and not because the optimization reached convergence. When this occurs, the analyst should save the timings and run the optimization again until convergence is reached. The final timings and reports should be reviewed to ensure that timings cannot be tweaked by a few seconds, so that all movements are operating under capacity or at acceptable levels of service. Now that the analysis is complete, the report can be printed. One report should be printed for each intersection. For ODOT projects, the full report must be submitted. To generate the correct report, under the Reports tab, the full report should be selected. This report contains the input data, the results summary, and the graphical report summary. One of the benefits of building a network in HCS is that it can easily be converted to Transmodeler. By clicking on the Transmodeler icon, shown here under Edit on the toolbar, the file is easily converted to Transmodeler. Transmodeler will open into a simulation run. The analyst should be careful when using this conversion and should check all lane configurations in Transmodeler to make sure they converted correctly and that the geometry of the lanes is smooth and realistic. There are several resources available to the analyst when using the Streets module in HCS. The Signalized Intersection chapter of the Highway Capacity Manual details the necessary inputs and provides more information on the why behind the analysis. Section 6.2.2.1 of the OATS manual provides guidance and standards for ODOT projects. At any time, the user may access the HCS Help Manual to seek help on a specific topic or input. Lastly, McTrans, the maker of HCS, has online video tutorials that go into more detail for completing analysis using Streets. A signal timing optimization tutorial video is also on the McTrans website.